This is the second presentation I've given at SNIA this year. The first one was on STT-RAM, and of course this one is on hard disk drives. I like to think of myself as covering the waterfront, okay? If there weren't so many great presentations on flash, I'd also mention flash, but I'm outclassed here. I'd like to talk about an interesting device that has been given a lot of, yes?
Yeah, put your lab on the microphone piece. It's in the actual base of it.
I hope you're not going to cause any problems.
I'll do my best. The microphone is not turned off, so I think
Okay.
it needs to close.
How about now?
There you go.
Okay, should I start over again?
Please.
No. I'm not going to talk about flash. I'm not going to talk about STT-RAM. But I am going to talk about magnetic hard disk drives. Ladies and gentlemen, this technology has been mentioned in the past as something perhaps we want to avoid or replace. It's true. It's a 60-year-old technology. 60 years. You know, that's probably longer than most of you have been on this earth. What I'd like to talk about today as a disk drive technologist is what is in store for this device, okay? And what can we expect in the next 5 years? But I'd like to start by talking about my last slide. I'll make a prediction. 80% of the bytes that will be used and shipped in the next 5 years will be from magnetic hard disk drives. 80%, okay? And there's a very good reason for that too. But let's move on. Well, these are the components for those of you who know this very well. This is a complex technology. It's electronic, it's mechanical, it's magnetic, it's everything, okay? It's everything all in once. It has one purpose in mind, to store bytes cheaply, reliably, and its availability is, I believe, unsurpassed. We're shipping a lot of bytes, and I'm going to make a prediction on what's going to happen in the future. It's true that the number of bytes shipped has gone down. I believe that's due to the fact that as users, you all have become very efficient in what you're storing, not only at the laptop level, okay, but also at the system level, okay? And I believe that cloud storage is one of those. This chart does not mention something called IoT. Somewhere, those bytes have to be stored, and there's going to be a lot of them. I predict that this chart is going to change radically in the next 5 years as more and more IoT bytes become available. We don't know that yet. If anybody in the audience knows what the byte ship will be for IoT, please see me after the presentation. I'll amend the chart accordingly. I love to change my charts. Hard disk drive designers are faced with a magnetic technology trilemma. It is a trade-off between what the write head can do magnetically, what the media can do as far as storing the bytes, and what the media can do as far as stability. And they are fighting this particular trilemma in every design. And the first and most important technology that I believe that is on the horizon is something called HAMR. It's a technology that relies on the fact that if I can change the temperature of the media locally, I can write it very easily. And then when it cools down, that amount of information is locked in, it's frozen. HAMR is probably one of the key technologies that hard disk drives will require in the next few years. And to raise the temperature of the magnetic media, a small laser is part of the recording head. And I'll tell you, a lot of good people at all of the major hard disk drive companies, Seagate, Western Digital, and Toshiba, are all working on this, okay? The progress has been a lot slower than anybody would like, but there has been progress. First of all, it's a major disk drive modification, a major one, okay? It adds a laser element to the head, and that increases the mass of the slider, that element that flies over the disk. That's very important, okay? Because the mechanics of the system will change significantly. It involves a new magnetic media material called iron platinum with another alloy. We know a lot about the present alloy because it's been in use for many, many years. But this is a change, and it's a big change, okay? The media is a metallic media, and it's comprised of many, many small grains of metal, and those grains are very important as far as storage density. Oh, by the way, did I say that density is probably the most important feature of a hard disk drive, because density equates to cost. And for storage, everybody is interested in cost. No one is interested in an expensive technology that requires a lot of capital outlay. Nobody is interested in that. Or if they are interested in it, it's for very, very specific niche applications. The disk also has a layer of lubricant on it, okay, and that must change. And it has the ability to increase areal density. And areal density is capacity and cost, okay? And it's been in development for many, many years, okay, for 12 years. And it still is not available. This is a chart that shows what this situation looks like in the change in number of grains versus areal density. And as areal density increases, the area that the head reads and writes is progressively smaller and smaller and smaller to get the density, and that involves fewer and fewer and fewer grains. And that is a significant challenge. Now, this chart indicates what we expect to get from new technologies. LMR is the linear magnetic recording, and PMR is the present technique in which the magnetic orientation is vertical with respect to the surface of the disk. And as areal density increases, hopefully the technology known as HAMR will allow us to use larger grains, which are more controllable, as areal density increases. Is areal density will increase? Hopefully we'll talk about that. This is another indication, because we know that the sensing element, the head flies above the surface of the disk, aerodynamically flies, okay? And that determines the magnetic spacing, the spacing between the sensing element, the read-write element, and the disk. The closer the element, the higher the field, the larger the field, and potentially the higher the areal density. Now let's talk about shingle. Shingle. Shingle is a technique that involves erasing a part of the track with a subsequent track, okay? It's a very, very interesting technology, and it allows us to increase the track density. So therefore, it is a writing phenomenon, not read, we'll get to the read, but it is a writing phenomenon. Now, if I may, hopefully we can get an animation to work here, but I'm not sure how this is going to, nope. maybe what I can do is, if I could have some, my help has left me. I want to move the cursor onto this dark box here, okay? Or the cursor, hit the cursor on the dark box, right there, no. Doesn't seem to be working.
Are you connected to the internet? Oh, there it goes.
Okay,
Can you take this, put it down next to the speaker?
yes. Okay, this is the right phenomenon, in which a portion of the track is erased by a subsequent writing of the track. Everybody like Yanni? The problem isn't in writing, it's the rewriting, okay? Because for some reason, a track may be buried in a group of tracks. And therefore, it's very difficult to rewrite the track that's buried there. There's a way around that. And that is to actually take that entire track and move it into a portion of the disk that is unwritten. Erase that track, and then move everything back again and rewrite the new track. What is the penalty for that? There was a performance penalty for that, moving data around. It's like Flash. When you start moving data around, you pay for that, okay? Now, I'm not particularly concerned about that because in certain applications in which rewriting is a rarity, okay, like cold storage for cloud or a large data center, that may not be a problem. Okay, I'll put this back on so you can hear me. It has the ability to increase areal density by about 15%. Does that seem like a lot? Believe me, it's a lot, okay. We talked about partial erasure. Writing is easy, but rewriting is difficult, okay. There is a performance penalty, and perhaps there is a problem with customer acceptance of this new technology. Now, I'll make another statement and prediction. This technology should be part of the disk drive, and should be transparent to the user. I mean, as users, who cares whether things are shingled or not? You're interested only in capacity, and you're interested in cost. And therefore, shingle should be an ideal case for that during the writing process. Now let's talk about another technology, two-dimensional magnetic recording. We talked about writing as shingling adjacent tracks, but somehow these tracks become so narrow. Again, you want higher density, you want lower cost. It becomes extremely difficult to separate one track from another track interference. And two-dimensional magnetic recording is a technique to modify the head so that not only do I read one track, but I read the adjacent tracks, and therefore with the proper electronics, I can factor out any errors. And that assures that I have a high capacity and also a very low error rate. Two-dimensional magnetic recording is in the works today, and many people are working on it. There's another technique called microwave-activated magnetic recording. It's a technique in which I put an element within the head to generate a field that allows the information to be read and written at progressively smaller technologies, okay? There's a couple of problems with that, but it looks very interesting. My prediction is that this will probably not be implemented. cost. Well, today, the cheapest storage technology that one can get at the desktop level is magnetic hard disk drives. It's somewhere of the order of perhaps less than a tenth of a dollar per gigabyte, of the order of 0.04, 0.05, somewhere around there. It's cheap, and that's why everybody loves it, okay? They love cheap things, okay? Again, we're talking about storage. It is probably a factor of 4 to 5 less expensive than flash. That's the common version of flash. There are other versions of flash, and I don't need to be critical about flash, but there is high-performance flash, okay, that is very, very expensive, okay? But I believe that all of those costs will progressively get better as we approach 2020. Will the two ever cross each other? In other words, will flash be as inexpensive as magnetic hard disk drives? I don't think so, okay? But it is an interesting idea. We've made a lot of progress in storage, both flash and hard disk drives, and this chart indicates that. So I think we could all be congratulated that we're providing the world with very, very inexpensive storage capability. This is just another small chart of that, okay? Now, helium filled. We're implementing that today, and that increases the disk drive capacity, and it reduces the cost of ownership because it increases the areal density. And how does it do that? Well, it does that because I prefer to use my own. It does that because what it does is it fills the disk drive with another ambient, namely helium, which has about 1/7 the density of air. And therefore, there's less drag force on this, there's less drag force on the element that moves, okay? And it allows closer disk-to-disk spacing. Remember, that increases the field and therefore potentially increases areal density. And it exhibits a more thermal conduction because helium has a higher thermal conductivity than air, less acoustic noise, it's quieter, and it reduces the dynamic forces on the disk. And this is an indication of what a disk looks like that's shaded for stress. And believe me, there's a big difference between helium filled and air filled, okay? And most disk drives today will start to use this new ambient. And I think it's a fairly interesting innovation. And these are the principal constituents of what spacing is comprised of. Notice that the areal density, we're talking about somewhere in the range of a terabit per square inch today. So areal density is somewhere in that range for magnetic hard disk drives, okay, which is phenomenal. And this is an indication of the physical spacing. We are flying of the order of somewhere between 4 to 5 nanometers, okay, a billionth of a meter. Okay, this is a summary, non-volatile memory products. Well, this is the lineup, and this is what we have to work with today, okay? Hard disk drives. My projection is that before 2020, we will see a 20 terabyte drive, okay? There's every indication. The drives today are already 10 to 12 terabytes. We'll see a 20 terabyte drive. There's no doubt about it, okay? As far as flash goes, well, we've made some surprisingly interesting changes. Flash per chip will probably reach well into the gigabit range, before the start of 2020. If I ever reproduce this chart again. Hopefully I'll include 3D flash, but so far the producers of 3D flash have been very secretive about their information, so I haven't been able to increase that. And I understand why. There's a lot of competition there. However, we also will see a lot of innovation as far as packaging goes for flash. And we've already seen that, okay, very, very high capacity packages on flash chips. I talked about STT-RAM. It's a very promising technology. We're going to hear much more about that, okay? I believe that hopefully in the future, we'll hear more and more about an STT-RAM storage memory and maybe logic too, okay? I mean, this conference is a storage developers conference emphasizing storage. There's no reason why this technology should have application to magnetic logic. And many, many universities and also many companies are working on that. Those are the other technologies that are very, very important. Progress is being made, and we'll hear more about them in the future. Areal density. Well, we're in that range of 1 to 2 terabits per square inch now for disk drives. And if you take the size of the flash chip and divide that into the capacity, you get areal density too for flash, although probably very few people talk about that. I would love to put 3D on this chart. As soon as I get the data, I will. But you can see that there's a lot of close following of both flash and hard disk drives, okay? And the costs appear to be at least parallel, if not converging. This is just a exploded view of that. Okay, bit pattern media, that's another one that you may hear. That technology relies on the fact that I attempt to personalize each media, each disk, with a specific pattern to increase data density. The problem with this is that there are 1 million disks per year for hard disk drives produced. 1 million, maybe more, maybe 1.5 million last time I looked at the numbers. To personalize that number of disks for a hard disk drive on 2 sides, because the disk stores information on both sides, that is formidable. Now I have to add a little footnote to that, okay? Please excuse me if I sound prejudiced. But if all of the bytes that I've talked about, okay, that are now directed towards magnetic storage, if those bytes are now directed towards a silicon technology, perhaps flash, ladies and gentlemen, there aren't that number of silicon wafers in the world today. There aren't. And if a producer, a manufacturer, wants to create a silicon factory, okay, to produce that number of solid-state devices, they would be best advised to convert that plant to logic, because there's more money in logic than there is in memory. So that's a trade-off, but perhaps we will see that, and I could be wrong, okay? Okay, this is a summary chart of technologies, okay? We've implemented helium, shingle write, 2-dimensional magnetic recording, I believe is in development, but I believe that that will be implemented, okay? And I believe that disk drive designers will try to put in another disk into these very high capacity large drives, okay? HAMR is still in development, damn it. But it will probably happen, okay? It will probably happen. A lot of good people are working on it, okay? And as far as bit pattern media and microwave recording, I believe that those will be in development forever. I don't think that they're implementable. What is all this going to mean It means that if I have a 20 terabyte drive, I can create a system that with at least a large number of drives that will start to store exabytes of data, okay? Now, a flash buffer or a flash unit to support that is very, very reasonable to assume. But this is the direction of the future, and I believe it will probably occur even before 2020. So in summary, I believe that disk drives are going to dominate the market for some time to come. This old technology, 60 years old, anniversary this year, I believe. Okay. Although I believe that the designers of the first disk drive would not recognize the drive today. It's changed so much. It's too different. It's much better. I think that disk drives and magnetic hard disk drives will continue to be the low-cost technology for some time to come. I believe that the products will continue to migrate to cloud storage. Cloud is a natural for magnetic hard disk drives. It's a natural. Okay, and I said that 80% of the storage bytes today are hard disk drives. There are significant technology challenges. A lot of good people, okay, some of them in this audience, maybe all of them, are working on this today because this is a multi-billion-dollar business, okay? And conservatively, I expect areal density to increase about 10 to 20% between now and 2020. Thank you very much.
We have some time for questions for Edward. Okay, back in the corner here. Hang on.
Can you comment on sort of the future of the shingle drives in respect to sort of this new innovation of, say, HAMR? Like, am I going to see a shingle HAMR drive or pattern media HAMR shingle drive?
I think the question is to comment on the viability of shingle and HAMR. Is that correct? I think I sort of indicated that, but my opinion is that disk drive users are going to be reluctant to trade off between capacity and performance unless there's a significant difference in those two. You get a lot of capacity for a little penalty in performance. My judgment is that if shingle can only be implemented if it's transparent to the user other than the performance hit. And if it requires the user to modify his operating system, it's a lose, okay? I learned this from another technology called 4K data sectors, okay? We learned that, okay, that if you tell the user, oh, by the way, you have a 512 byte data sector now, but now change the operating system to now operate at 4K, the user will say, well, what does that buy me? I don't know if I want to go back and change my operating system. So what we did was we made that transparent. The drive itself takes the 512 byte sector data and converts it to 4K. And that is the standard in the industry today, and we learned that. And hopefully all the good people that are working on shingle and the standards, he's standing in front of me right now, he knows that, okay? And he can tell me that we know that very well. Yep, HAMR. You know, HAMR is a very large change in the disk drive, okay? But we've been working on it for a long time, and I believe I'm seeing some progress, okay? That's the good side. It's a monumental change in the drive physics. The questionable side is something called power. And I believe that in the future, and perhaps it's happening today, that a technology will be selected, not because of its performance, reliability, and cost, but because of its power dissipation and how much energy it stores, particularly for a very large data center type application. And I know of cases in which people want to build a data center and they can't because they can't get enough power to power it, okay? That doesn't speak too well of hard disk drives or flash either, okay, which also uses some power. Not a lot, but some. And therefore, it opens the door for a technology called STT-RAM, okay, which doesn't use that much power. Yes, sir.
Hey, Rob Johnson from Stony Brook University. So SMR, introduced these problems you mentioned where you have to solve them at the algorithmic level by doing garbage collection and moving data around. Is HAMR going to do that? Are there going to be some problems that have to be solved in the firmware or in the operating system, or is it basically going to be just this new technology on the disk head, but things still run exactly like they did other than that?
I'm not sure how I can answer that easily, okay, without saying the wrong thing. My judgment about shingle is that we may reach a track density in which the head cannot function at the error rate that we want it to function. And therefore, that's why people are working on two-dimensional magnetic recording, okay, to solve that problem and create a different type of head that's not subject to the high error rates, okay. Now, HAMR directs itself at another situation, the magnetics of the problem, not the dimensions, but the magnetics and indirectly dimensions, okay. Again, the problem with HAMR is it's a very large change in hard disk drives, very large change. The largest that I can remember. It changes the media, it changes the head, it changes the mechanics, but I am still confident that that can be done. The technology is too important not to give up on that, okay, that particular technology. I could be wrong, but I know the people that are working on it, they're positive, so I have to be positive too.